Welcome everyone. From now onward, we'll start Unit 2, which will discuss in detail various styles of constructing different kind of combination and sequential circuits out of the NMOS transistors and NMOS and PMOS transistors. In Unit 1, we went through the basic construction and the basic operation of NMOS PMOS transistors, including the formula for the current consumption. Unit 2 will look into detail of different styles used for construction of different gates. The first chapter of Unit 2 will discuss. We will see. Let's see the outline of this. We will see different types of. We will see some examples of complex gates which are designed using static CMOS circuits. We look at different kinds of. We look at tri-state inverters, tri-state buffers, different kind of muxes, inverting and non-inverting. We'll see how pass transistors and transmission gates are used. We'll see an example of a layout of a slightly bigger circuit and also an inverter. And I'll try and point out, we discuss the important parts of the layout so that we understand how the capacitances are minimized during the layout. Look at there are a couple of slides about stick diagrams. Stick diagrams are very useful when you want to represent a layout on a paper. So let's start with the CMOS gate design. I would recommend during this and other Unit 2 lectures to have pen and paper ready so that you all are able to quickly draw the circuit on your paper. That will be very helpful in understanding the design. So this is the first activity which I want you all to do. Get a 4-input CMOS NAND gate. This should not be very difficult considering we looked at 2 and 3 input NAND gates in Unit 1. So just to review that, a NAND gate, there will be two parts of the circuit. The pull down will be connected to the ground, which will be comprised of NMOS transistors. The pull up part will be connected to VDD, which will be comprised of the PMOS transistors. Each input of any gate will be connected to two transistors, one NMOS and one PMOS, that is to the gate input of that. So a 4-input NAND gate will have 8 transistors, that is 4 pairs of PMOS and NMOS each. The pull down network, that is the NMOS, will represent the complement of the function we are trying to calculate. So on AND, the pull down will become the AND and all the NMOS will be in series. The PMOS represents the complement of NMOS, so all the PMOS will be in parallel. So let's try and draw this circuit on the paper. Correspondingly, what I would do is we'll see a 4-input NOR gate. So you could also say that the NAND gate will be complement of the NOR gate. So let's review the NOR gate also. So as I said that each input, let's say A for this in this example, will be connected to 2 transistors, one PMOS and one NMOS. It will be connected to the gate input of the both transistors. The pull down network will be connected to ground. The pull up network will be connected to VDD. The pull down network shall represent the complement of the function we are trying to implement. In this case, the function we are trying to implement is NOR. So the pull down network of NMOS shall represent an OR logic. That means all the NMOS here will be in parallel, which is the case here. Similarly, the pull up network, which is connected to VDD there, will be the complement of the NMOS of the pull down network. Since all the NMOS are in parallel, the PMOS shall be in series. So VDD is connected to PMOS 1 and PMOS is connected to PMOS 2. And the output for this kind of circuit is always taken from the common drain or whatever drain or source you want to call it. the Y here will be connected to this gate source. So the convention says that whatever is at higher voltage shall be called the source. We'll call this point source of these transistors. So Y is connected to the source of, or it will also be connected to two points. That is, one is the source for all the NMOS, other one, let's say, is the drain of all the PMOS circuits. In this way, you could construct simple gates as many with as many inputs as you want. So just remember two important points. Let's see on the next slide. So we call this type of circuit as static CMOS. Why static? Okay, static because in steady state, that is, whenever the values on all the inputs are stable, the output will be either tied to 0 through the pull down network. Through the NMOS pull down network, the output will be either 0 whenever pull down is on, and whenever pull up is on and pull down is off, the output will be tied to 1 through VDD. The inputs drive the gate inputs of the transistor. Please be very careful in noting down that the output is not directly controlled to input. The output is always driven by either VDD or ground. What this means that if, let's say, there is any noise on input, let's say the inputs are such that the output has to be 1, that is connected to VDD, and if there is a little bit of noise on input, within the noise margin, we'll see what noise margins are later, but if the noise is within the noise margin, the output will not see any noise since it's not driven by input directly, it is driven by the VDD or ground. Another thing to let's see this quick table. So whenever pull down is off, so this represents like whenever pull down is off and pull up is off, that is this quadrant, the output is Z, that is, it is neither connected to VDD nor connected to ground. Now this case will not happen in case of a static CMOS. Why? Because we are assuming that all the inputs are driven to some value, and since PMOS and NMOS are complement to each other, the case of both being on or both being off will not usually happen. These two quadrants are valid cases. So whenever pull up is on, the output is connected to VDD. Whenever pull down is on, the output is connected to VDD. Now also notice one thing, that in the steady state, that is whenever the inputs are not switching, the output will draw almost negligible current. That is, if it is connected to VDD, the resistance, the on resistance of a transistor is quite low actually. So it is drawing very negligible amount of current from VDD. Similarly, when it is connected to ground via NMOS, it is sourcing it is sinking very negligible amount of current. What this means is that this kind of circuit is very power efficient. When we see different logic styles in later chapters, please try and differentiate between this logic style and other logic styles on the basis of power. Now NMOS and PMOS independently also are switches, so they can be used to make the different type of gates. One of the examples, this is not a very popular style. We'll come to this why is it being so in the next slide. So when NMOS is on, when NMOS the gate input is 1, the NMOS is on. When the gate input it is 0, the PMOS is on. So let's look at figure A. So A is connected to B by a series of two transistors. They are both NMOS. So whenever both G1 and G2 are 1, A will be connected to B. So you could say that the function being represented here is G1 and G2. So there is a simple truth table of an AND gate. Similarly, when we look at the PMOS, so PMOS would again be the complement of NMOS. So whenever both of them are 0, then only the gate will be on. So this represents an AND gate. Here we see that the circuit of two NMOS transistors in parallel. So when either of G1 or G2 is 1, A will be connected to B, which is this case, and this case, and both have an output. A will be connected to B. Similarly, the fourth figure is nothing but the PMOS and complement of C. Now, again, the important point to note here is that G1 and G2 are controlling signals, and if the and A is in some of the cases, whenever there's a path exists from A to B, A is the input which is connected to the drain, and B is connected to the source. So in some of the cases, the path exists between A and B, and considering, let's say, the output is B, and the other way around also, the output can also be A. So A and B are connected with each other in some of the cases, which means that a noise signal on A would be passed on to B. This is an important point to consider in this case. This kind of circuit, building whole gates using this style is not very popular because of the reason I said, because the noise gets passed easily. Now, as I discussed earlier, I would like to repeat this point that a complementary CMOS gate will always produce either 0 or 1. The rule of conduction complement says that the pull-up network is always the complement of pull-down network. What it means is that if the pull-down network is series, the pull-up network will be parallel, and vice versa. You can see any of the circuits we have discussed earlier, either 2-input NAND gate or 2-input NOR gate or 3-input NAND gate or 3-input NOR gate. Always the pull-down network is the complement of pull-up network. This makes our job very easy when we want to construct complex gates. We will see in the next slide. So here is one of the compound gates. It's a very popular gate, and or invert. So the notation which is being followed in the industry is A is for AND, O is for OR, I is for invert. So this gate is AOI22. Now any compound gate that is doing an inverting function. Now please remember that CMOS logic by design is an inverting logic. What it means is that, let's go back a slide and see a 2-input NAND gate. So a 2-input NAND gate would need per input 2 transistors, in total 4 transistors, but the function of Y is A dot B AND. If you want an AND gate, you would have to add one more stage of converter after Y. That would mean that AND gate would have a 2-input AND gate will need 6 transistors. So whenever we discuss compound gates, it's easier to discuss the gates which have inverting function. That is, Y will be complement of some function. In this case, Y is complement of A dot B plus C dot D. Now a non-inverting function can be implemented just by adding an inverter at the output of Y. So most of the compound gates that we discuss in the coming slides will be in the form of Y is equal to complement of some function. So converting it to a non-complementing one will be simply adding an inverter. So let's look at this. Now A dot B plus C dot D. Now what we could say is that is the non-complementing part, that is A dot B plus C dot D. We can easily construct the pull down circuit with it, and pull up will be simply complement of that. So let's look at figure E. So figure E, we see that A and B are in series. So A dot B means A and B are in series. Similarly, C dot D means C and D are in series. A plus sign means an OR of both. So here A dot B and C dot D are in parallel, and this is a pull down and will be connected to 1. Now when we try and do the complement of this, we are left with almost a similar sort of structure. So A dot B in series here would mean that A and B are in parallel. C dot D in series here means that C and D are in parallel. A complement, a plus sign would here mean that the two are in series. So what would help is in analyzing the circuit is writing down on paper the complement of this. So now let's look also at the smaller part of the circuit. Let's say A, so A B in series. Let's do this. A B plus C D in series. So A B are in series. C and D are in series. A plus sign would mean going from A to B. We'll add a plus sign, that is an OR. We'll combine A and B and C and D to convert an OR function. Then we go on to C. Now so A and B will be in parallel. C and D will be in parallel. When we combine them, we just connect the part here. We just connect the part here to the part here. So what would that mean is that C is connected to A and D is connected to B. Now with a connecting wire. Where does this wire come from? This wire is common to this point and this point. So we get E. This is the logic diagram of this circuit. So please take a moment to review this circuit, review the construction of this compound gate. I'll have one or two more examples. Okay, let's move on. This is one more example of O3AI. What O3AI means is that it means OR of 3 inputs, and the output of that will be ANDed to one more input, and invert is the default. The logic function is y is equal to A plus B plus C, OR of all these, and into D and complement of this. So this is a circuit. Let's again review this. For pull down, we should look at the non-complement part and implement as it is in NMOS. A, B, C being in parallel, A, B, C being in parallel, and the whole circuit should be in series with B. The whole circuit is in series with B. For the pull-up part, A, B, and C should be in series, and the whole of it should be parallel to D. Whole of it should be parallel to D. We could also see and apply inputs at each of A, B, and C to see if it really satisfies Y. So let's say D is 1. D1 means this NMOS is functional. This is connected to Y, this part, and then when either A, B, C is 1, or any of these is 1, Y would be connected to 0, which is in turn satisfied by this equation. D being 1 and any of A, B, or C is 1, Y would be complement of 1, which is 0. And we should also verify correspondingly that this circuit, since only one of the pull down or pull up can be operational, let's also verify that with the same conditions this part would be off. So when D is 1, this is off, and when any of A, B, and C is 1, this whole part would be off. So you don't get a connection from Y to B, which is the basic principle of this kind of static CMOS network. At one given time, only one of the pull down or pull up can be active. Now let's come to signal strength. The strength of the signal. Now let's say you have a network of gates. Each in any of the design you will have a typical VLSI chip contains billions of transistors. Billions of transistors means millions of hundred thousands of gates. A lot of gates are connected in their multi-stage network. That means that there will be, let's say, an AND connected to OR connected to an inverter and so on. So each of those gates, each of the outputs and inputs of those gates, we have to see they should all be relatively strong. That means to make sure that the functionality of the whole digital design is correct. So we have to see, so each of those inputs and those outputs, when we say how strong is the signal, we mean to check how strongly does it approximate the ideal voltage source. The ideal voltage source in this case being VDD and GND rails. VDD and GND rails are supposed to be strongest, are sources of strongest 1 and 0. How strong? What does a strong mean in quantitative terms? Let's say in my chip the VDD is 1.0 volt and GND is 0 volt. So a strong one would mean a voltage value which is very close to VDD, that is 1.0 volt. How close? Let's say 5% of, let's say it should not be worse than -5% of VDD. That means a strong one would be somewhere between 0.95 to 1.0 volt. Similarly, a strong 0 would be between 0 and 5 millivolts. We saw earlier that NMOS passes a strong 0. That is why it is used in a pull down network. But it passes a degraded or weak 1. We also saw that NMOS, while passing 1, it will the VT of the transistor will be subtracted from VDD. So a VDD at the source or drain, at the drain would, and the gate being also tied to VDD, would mean the voltage on the output, that is source, is VDD minus VT. Similarly, CMOS will pass strong 1, that is why it is used in a pull-up network, but degraded or weak 0. Right? Now, with that thing in mind, we will review the pass transistors and the usage of them in switches. We've seen this earlier, but the discussion of pass transistor is important here to see how transmission gates are constructed out of them. So again, let's go through the pass transistor. Pass transistor, what it means is that the input is being applied at source and the output is being taken at drain, or vice versa. So if gate is 0, source and drain for NMOS are disconnected. If gate is 1, if the input is 0, if the input at S is 0, the drain would be strong 0. If S is 1, the drain will be a degraded 1. What it means is S is VDD, the drain would be VDD minus VT. Similarly, whenever PMOS is on, if S is 0, the output is degraded 0. That means output will be DSS plus absolute value of VT of the PMOS transistor. When the input is 1, it will be a strong 1. Now what we do here is that from the pass transistor, we combine the NMOS and the PMOS. So NMOS passes a strong 0, PMOS passes a strong 1. We saw that static CMOS gates, they utilize this functionality to make sure that output is always a strong 0 or strong 1. And how did they do that? By making the pull down complement of the pull up network. Now here, while construction of transmission gate, we connect a PMOS circuit here and an NMOS circuit here. By the we connect both the source and both the drain together. This was not the case in static CMOS. Please note. Here the input is not coming from the gate. The input is coming from the source side and going to B. B is the output. Now let's see how this functions. whenever now please note that one input is connected to the gate G, other is the complement of gate G is nothing but complement of G. Whenever G is 0, the NMOS is off, GB is 1, the PMOS is off, A is not connected to B. Whenever G is 1 and GB is 0, they both are connected. What it means, if the input is 1, the PMOS here makes sure that output is strong 0, although there is connection also via NMOS, but the PMOS makes sure that the output is strong 1. Whenever A is 0, the NMOS makes sure that the output is strong 0. So we utilize the properties of both NMOS and PMOS to construct a gate, a switch, in fact a simple switch, which makes sure that output is not degraded. This is the symbol of these are the example of symbols of A and B of the transmission gate. So in transmission gate we have three symbols: the input A, output B, and the controlling gate input G. But we also need the complement of G, which is G. Let's see how transmission gate is now used. Now we realize that a transmission gate can be a good switch. Let's see how do we use it to make big circuits. One of the most famous circuits is a tri-state buffer. Now a tri-state buffer produces so in fact the switch we saw here, this switch is nothing but a tri-state buffer. So a tri-state buffer has an enable pin, so the G is now labeled as enable, and both enable and enable complement are available. Whenever enable is 0, the output, we saw it's not connected to input, and we represent the output, the logic level on output to be Z. The Z is a tri-state, that means it is either connected to VDD or VSS, not the ground. Now whenever enable is 1, it simply acts as a buffer. A 0 on A would mean a 0 on Y, a 1 on A would mean 1 on Y. Now let's compare this to a basic static CMOS circuit. So let's compare the two different styles. Now the basic gate in CMOS static circuit was an inverter, which had two transistors. So Y was the complement of A. And PMOS and NMOS are not. I mean, let's say the source of one is connected to drain of other. Now, in case of transmission gates, the basic gate here is not an inverter but a tri-state buffer, and it has a one separate input called the enable pin. It also uses two transistors, but the basic functionality is that of a buffer. However, this also needs the complement of enable pin, which should also add, let's say, one inverter and two transistors. So the basic gate in case of a transmission gate is a buffer. The basic gate in case of a complementary CMOS is an inverter. Now we call this kind of a transmission gate as non-restoring. Why non-restoring? Is that because the noise on A is passed on to Y, as we discussed earlier, because whenever enable is 1, whenever this gate is enabled, since the sources are connected to drains, both of these NMOS and PMOS are conducting, a noise on the source of a transistor can transform into the noise on a gate of the transistor. So any noise on A will pass on Y. So it is known that the tri-state buffers are noise prone with such a construction. Okay, now there's one more slight modification onto this tri-state buffer, and we make out a tri-state inverter out of this. Let's see how we can do that. Tri-state inverter is a very popular style of logic design. It is used heavily in construction of muxes. Let's see how. And plus it is also restoring. That means the noise is not passed on to the output. Let's see how. Now what we do is, okay, in the previous slide I want to mention one thing. It says that a transmission gate needs only 2 transistors, which is not exactly true. Yes, it needs 2 transistors, but it is assuming that the NOT of enable is already available. Now what we do here is that we connect the enable. We make, let's say, this the part here. This part, what does it represent in isolation? What it represents is that these 2 transistors here, this PMOS and this NMOS, they represent an inverter here. But the same input is not connected here. NMOS is connected to EN and PMOS is connected to EN bar, just like in case of a transmission gate buffer. A single input A is connected to PMOS here and NMOS here. What it means is that, what it means is that whenever enable is 1, this is turned on. This is also turned on because enable is 0 here. Enable bar is 0, and it's a simple inverter. That means this whole circuit, this transistor here, this transistor here, and this transistor here, this circuit now is just an inverter, simple inverter. And whenever enable is 0, this is open and Y is Z. So again we notice 2 things here. It violates conduction complement rule. The pull down is not the conduction, is not the complement of the pull up. Why? Because we want a Z output. Second important thing is that noise on A is not transferred on Y, because A is driving the gate input of the transistor. This is the symbol, the logic symbol of a tri-state inverter. You can either represent it by this or by this. In the case of the first one, it is implicit that a conduction, a complement of EN is available. In this case, we are making the connection explicit. Okay, so just a few important things to remember. A normal CMOS inverter, a transmission gate buffer, and a tri-state inverter. So we see all these 3 basic gates. Now we see how tri-state inverters are used. Right? Now I mentioned that a tri-state inverter is most popular in construction of muxes. So this is the case. Let's look at a 2:1 mux. Let's review the mux functionality. Whenever the select pin is 0, no matter what happens on D1, the D0 will be passed on to Y. So select is 0, Y will get whatever is present on D0. Similarly, when select is 1, Y would get whatever is present on D1. Now let's say if you would want to construct this mux out of a complementary, out of a static CMOS design style. So what we would look for is, we would look for first of all the Boolean expression. Now y is equal to SD1 plus S bar D0. Now as we notice that any function should be in form of a complement, so we could say that y is equal to, we could add a couple of complements here, 2 complements, and we could construct a pull down network out of. So let's first see how now we could for constructing the static CMOS circuit. This the complement, the first complement here, the topmost complement would mean adding an inverter at the output stage, and the remaining circuit here, the complement of SD1 and SD bar, this remaining here would go down as a pull up and a pull down network, right? So let's see how many transistors are needed. The answer is 20. You could go back and verify. Let's see how 20, why 20. So this would mean AND gate and inverter and an AND gate. Here we have done some bubble pushing here to convert this and into a NAND, adding an inverter and again adding an inverter. So a 2-input NAND gate. If you go back and remember, the 2-input NAND gate needs 4 transistors. So and in turn would need 6 transistors because one more inverter is added. So we have just labeled the number of transistors. So each NAND requires 4. Additional inverter requires 2. Again, a NOR requires a 4 and a 2, and an inverter 2. So in total, this mux would need 20 transistors to implement. Now let's look at the power of transmission gate. In specifically not transmission gates, in fact, a tri-state inverter. So or let's first look at transmission gate. Now a non-restoring mux, we label this as non-restoring because again it's transmission gate based and noise on inputs will travel to output. That's why we say it's a non-restoring. So we need only 4 transistors. How come? Now both transmission gates can be connected. The outputs of both two transmission gates can be connected to the output, can be tied to the output. However, we have to make sure that only one of the transmission gate is active at one time. How do we do that? We make sure by connecting the inputs, the enables in such a way. We have connected S here, and we have connected S here to the bubble. But here in the second case, the S is connected to the non-complementary. Similarly, S bar is connected to the bubble here, and S bar is connected to the non-complementary input here. What this means is that the enable or the S connections to the top transmission gate and to the bottom transmission gate are both complementary. What it means, if S is 0, the PMOS here is active, S bar is 1, the NMOS here is active, so this path is moving. If S is 0, if S is 1, in that case this is switched off. Why? Because S is 1, PMOS is off, S complement is 0, NMOS is off. Now this path becomes enabled if S is 1. So a transmission gate mux needs 4 transistors. If we compare apples to apples, this means we have to also take care that this S here would need an inverter. This S actually would need an inverter here. This S is connected here, and S bar will be available here. So this inverter means 2 more transistors. So 4 plus 2 6, and the earlier one had 20 transistors. The only disadvantage in transmission gate mux is the non-restoring part. Now let's see an inverting mux. What the inverting mux means? Inverting mux means nothing but the output is Y is just a complement of the earlier mux we saw. So Y would be nothing but the complement of the regular mux. So there's a bubble here. If you notice, there's a bubble here. Now if we use a simple AOI type of gate, then we see that we need 8 transistors to implement this using a static PMOS. How? Let's see the construction here. So let's so D0, let's look at the pull down first. So pull down, we have to see that the first S bar and D0 are AND together. So D0 here and S bar, this is an AND connection. Similarly, S and D1 is again an AND connection. Both of this is an OR connection. So this is an OR. This connection is an OR connection. Similarly, the pull up part would be a complement. We saw the construction of AOI 2 earlier. This is exactly same. Only the inputs are labeled differently. That is, earlier the inputs were A and B. Now they are D0 and D1. Or this is the first case. or what we could do is we could use a pair of tri-state inverters. We saw that this is the construction of tri-state inverters. Again, if we are connecting multi-stage tri-state inverters to construct a mux, then we have to make sure that the connections of S and S bar are complementary to the two stages. So S and S bar are connected differently here. D0 and D1 are connected in the same fashion. So this is very similar to this circuit we saw earlier, and also to this circuit we see here. Both utilize 8 transistors, but now this inverter, this inverted mux here is the restoring type, because all the inputs are at the gates. Let's look at still bigger multiplexers. What we saw earlier was a 2:1 multiplexer. Now let's look at 4:1 multiplexer. It chooses one of the 4 inputs, and there are 2 select lines. So again, it's going back to your digital design basics. 4:1 multiplexer can be constructed out of 2 2:1 multiplexers, with the LSB, the S0 controlling the 2 muxes here, and the S1 controlling the mux which controls the output. Now a very simple circuit of this is connecting 4 tri-state inverters to the output. Now please note that here for 2:1 multiplexer, this one and this one, these are 2 tri-state inverters connected. The output of both of them is feeding by. Similarly, for 4:1, there will be 4 tri-state inverters. Output, each of these outputs connected to Y. However, the enable will change now. So the lowest, the MSB, that is D3, will be S0 S1, D2 will be S1 S0 bar, again D1 will be S1 bar S0, and D0 will be S1 and S0 bar. Also note that we would need inverters here to get the logic level values of. So we need S0 and S0 complement, we need S1 and S1 complement. So we will need two inverters, one for S0 complement, other for S1 complement. So each of these, so in fact these inverters are shown here. So S1 direct connection. Again, this is the nothing but S0 bar. Okay. So we see that a circuit which has a very big, comparatively a bigger Boolean expression for a 4:1 mux is in implementation is actually not a very big circuit. It's just 4 tri-state inverters all connected in series to Y. This is the power of tri-state inverters in construction of muxes. Now let's review this. Let's see an exercise of construction of a complex gate. I would again request to do this, as the slides progress, to try and do this on paper yourself. Now, so this we have. It's very popular. Now you must all be clear how to do this. So the easiest way, what I would suggest, is to take the non-complement part, draw the pull down, and then take the complement and draw the pull up. In these slides, what we are starting with the pull up part. So we'll take the complement part. So we just do a Boolean rearrangement of this, and we come up with the pull up part. So what this means is that A and B would be in parallel. The PMOS, the pull-up network, A and B would be in parallel, ANDed with C or D and E. Let's look at the next slide. So this is how we do that. A and B are parallel. C is again in series with D and E being in C. Sorry, C is in parallel with D and E being in series, and these two are connected like this. This is the series connection that represents this ending here. This is the pull-up part. Again, pull down part, not very difficult, just the complement of this. So pull down part is nothing but the the non-complement this part, non-complemented part. Let's see on next slide. This is the non-complemented part. AB plus C, D plus E. AB in series, C plus D in A. We combine both the pull up and the pull down part and construct the pull circuit. How many transistors? We don't need to look at the circuit to calculate that. We have 5 inputs. That means 10 transistors, 5 pairs. So I would request you all to. So at the end of this lecture, given any Boolean expression, you should be able to draw a static CMOS circuit out of it. We also saw that not all CMOS circuits or CMOS designs are designed this way. We also use the power of transmission gate and tri-state inverter to construct circuits such as MUX. But still, this is the most popular technique for complex logic circuits. Okay, now look at let's try how after for a complex case we arrived at a static CMOS circuit. We now with the circuit in place, you know how many transistors it's going to take. Now let's see a very basic layout, how the layout is made, what things are taken into consideration. Each layout is a technology based. That means layout is a technology specific. That means a layout by technology I mean the channel length. That is, for example, if the channel length is 90 nanometer, there will be some set of rules which need to be followed. These rules come from foundry. For example, TSMC is the largest foundry in the world, based in Taiwan. So they will have, according to their manufacturing processes, they will have a set of rules which should be adhered to when we make the layout. So layouts, in fact, are very time consuming. The gates have to be fit together nicely. It's one thing to make a complex gate out of transistors, and it's another thing to lay them out. The actual area of the gate, how much space the gate occupies on silicon, is very much determined by how well it is laid out. So the basic methodology is that VDD and GND rails. When I say rail, I mean they are connected to the power supply, and there's a copper interconnect on the layout. They are called VDD rails, VDD and GND rails. They should abut. That means what abutment means is that each first of all these cells such as muxes, AND or inverts, NAND, NOR, latches, flip flops, combined we call them standard cells. The standard cells are the basic building blocks of any digital design. So usually what happens in industry is that already let's say our design team is making chips for the mobile phones, let's say. Now when they start making chips, they already have a library of standard cells, and either some team in their own company has designed all those standard cells and put them in place, or they buy it from any third party. But to start designing the logic, they need this standard cells, the libraries in place. We'll see much more of this in synthesis. So these cells are called standard cells, and a combination of all these cells is called a library. Now what VDD and GND, what abutment means is that all these cells should have fixed height, but they can vary in width. We'll see later why. This is the first major rule. Then adjacent gates should satisfy design rule. That means that there should be some minimum spacing between adjacent gates. Always the convention is that NMOS at bottom and PMOS at top. So the NMOS, the pull down network, will be connected to ground, and PMOS will be connected to VDD. So VDD would be at top. all gates should include well and substrate contact. So in this case, when we draw a transistor based circuit on paper, we do not show the substrate and the well contact, but layout needs to show that, because layout is the one that goes to foundry for manufacturing. The circuit on paper will not go to foundry. It's only the layout, and that too in a machine readable binary format. It will go to the foundry for manufacturing. So all connections should be explicit and very clear. How good a layout is often determines how well the circuit can be manufactured, how well the design can be manufactured. Now let's see an inverter layout. We have already discussed this. The VDD and the ground rails run parallel to each other. There will be one fixed height. Now let's say I am designing this inverter and I also want to design an AND gate or NAND gate. So I have to make sure that all of the gates I design will have same height, so that an AND gate here, let's say I construct a circuit now of an AND gate. So how would I do that? I would make a NAND gate here, which would be connected to this inverter here. So the VDD rail, if continued here, that is why I need to keep the height same, so that both of these cells can be placed between VDD and GND rails. So VDD and GND rails, the space between them determines the height of all the cells. Right? They should be same for all the cells in the line. There are exceptions, but only for very complex gates, but not usually. That is why we say that all standard cells should be of same height. Now in the B part here, we also show the explicit substrate and well taps. So the NMOS here would need a ground tap for substrate. A PMOS here would need the shaded gray area. This area represents the well. So there is a well tap. Let's look at a slightly more complex gate, which is NAND, a 3-input NAND gate. Again, how do we read a layout? So VDD GND rails are very clear. The pull down part, the gray part here is the NMOS diffusion layer. Let's see now. The pull down network here, this pull down network A, B, and C, these are all in series. So let's start from ground. Ground connected to C, not to C, sorry, not to C, but the ground connected to the diffusion. Again, so this is again diffusion connected to diffusion, again diffusion connected to diffusion, and again a diffusion going to 1. Correspondingly, in layout, we see ground rail, there is a contact, there is a substrate tap, connected to diffusion, 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 and then this goes to 1. The blue part here corresponds to the pull down network here. We see the pull up network. Now pull up network, VDD needs to be connected to 3 diffusion layers here. So we see now VDD, this gray part is the well. We cannot see the gray part here because again this gray is same as the diffusion gray here, so it's camouflaged. VDD here is connected to diffusion by a contact. Now see here in the pull down network, we notice that the contact is needed to connect it to ground, but the region here, this region and this region here has no contact because none is needed. Right? But here in the pull up case, the VDD is connected to contact, the VDD is connected to this contact, and if you notice, the VDD should be connected to all 3 diffusions. But what about here? What about in the layout? Now in the layout, the connection from A to B, the connection from B to C actually, the PMOS, this particular PMOS and this particular PMOS, they are both flipped, in the sense they both share this common VDD. Why is this? Because we want to minimize contact, we want to minimize the metal length, metal routing. So this is one way of doing that, is that VDD is connected to A here, and this now VDD is, this metal is being shared between B and C. Again, let's look at the inputs A, B and C. So inputs connect to gates. Now what are gates? Gate made up of, gate are made up of polysilicon. If we remember the unit 1, the construction of a MOS, the gate is nothing but a strip of polysilicon. Each input here goes to two transistors, a PMOS and an NMOS. So this A in layout is nothing but a wire of polysilicon. This is a wire of polysilicon connecting the gates of one PMOS and one NMOS. So A goes here vertically. Again B takes a D2. This is to satisfy some design rules. Again C takes a D2. So A, B and C are three inputs. Let's look at Y, which is the output. Now output is connected, again output is connected to NMOS here at the bottom and network of PMOS at the top. So Y here, let me clean this up a bit. Okay. Now so we see Y here is connected to the topmost. So NMOS are stacked. It is connected to the topmost here. So this actually, this layout and this the schematic don't match completely, because here in the schematic the A is the topmost stacked NMOS, but here we see that in fact C is the topmost stacked, so it doesn't matter. So Y is connected to this NMOS here, which is C, and again Y now needs to be connected to all three transistors at the top. So the connection to C, this one is the connection to C. This connection is common to both A and B. So we see that very intelligently VDD connections to all PMOSes and the output connection to all PMOSes, the connections for two transistors have been shared. This is to make sure that the number of contacts remain minimal. We will see one example later. Now this, the height is 40 lambda, we see is the feature size. So the height is 40 lambda, and this 4 lambda is nothing but a design rule which says that, an example of a design rule which says that there should be a spacing of 4 lambda from the other rule. Let's see, these are just, these design rules are just examples. They can be, these design rules are different depending on different technologies. So I hope everybody now can read a basic layout and understand a basic layout. Stick diagrams are a very popular way to help plan layout quickly. Since they are an abstract representation, they need not be on to scale. Obviously, to show different kind of layers, different metal layers, polysilicon, gel cap, you would need color pencils or different kind of crayons to draw this layout. You can do 1 or 2 exercises yourself on paper to make sure the concept is clear. So the A is an inverter layout, and B here is an AND gate layout. Different legends are shown on the right side. So contact is shown by black, metal is a white bar, and diffusion is a gray bar, and so on. Wiring tracks. So a wiring track is a space required for a wire. So an example could be of a design rule could be that a wire should be of 4 lambda width, and between two wire tracks there should be a spacing of at least 4 lambda. So let's define a new parameter called a pitch. A pitch is a combination of the wire width and the minimum spacing it needs. So the pitch of this wire is 8 lambda, that is 4 lambda is the width and 4 lambda is the minimum spacing that is required. So the height of the transistor can be represented in terms of wiring tracks. So for example, a design rule of this particular technology says that the diffusion should be at least 4 lambda high, and again this polysilicon wire is running between them. the gate, it should be at least 4 lambda. So a transistor is in fact taking more than 8 lambda, it's taking more than a wire track here. Let's see an example of one more design rule of well. So an example design rule could be that well should be surround the transistors by 6 lambda at least. So what it implies is that between opposite transistor flavors there should be at least 12 lambda, because you would need 6 lambda down here and again 6 lambda down here. So the distance between these two would be at least 12 lambda. What it again means is that if the distance is 12 lambda, you could actually draw a wire between these two transistors. Why? Because it satisfies the wire design. How do we estimate the area of a gate after the layout? When we are drawing the layout, we estimate the area by counting the wire track. That is, for example, for this kind of a gate, we could estimate the area by since the pitch of the wire is 8 lambda, we could multiply by 8 to express in terms of lambda. So let's say this is 40 lambda, so this is 5 wiring tracks, this width is 32 lambda, so the area of this gate is 40 lambda by 32 lambda. This is an example. We saw the construction of O3 AI in terms of static CMOS earlier. Now let's see this is the layout. I guess this is yeah. So this is the layout in terms of stick diagram. So I will not go into too much detail of this. I would expect all of you to first on the left hand side put the transistor level gate design, which is called the schematic. On the right hand side, you study this layout, this stick diagram, and satisfy yourself with this construction. You would see some interesting features here, that is sharing of contacts. So one thing is clear. One quick observation you could do is that you see now more taps on the NMOS when compared to PMOS. So you could say that the NMOS circuit requires more parallelism compared to the PMOS network. So since if the network is series, it would require less contact taps. If the network is parallel, since the parallel network needs to be connected to VDD and GND, each transistor gets connected in the parallel network, you will see more taps in the parallel network, right? So this is again estimating area. This estimating area is not it's not very easy doing it on paper. There are many tools available for layouts. Maybe one of the other electives or courses has layout techniques, and when you use these tools, you could actually estimate area. One thing is very clear. One thing is fixed. Let's remember that the height of a cell is fixed. So you would have to draw a layout within those restrictions, keeping the height fixed and varying the width depending on how many transistors are needed. So let's review the topics we studied in this chapter. We saw the construction of some complex gates using static CMOS techniques, and the static CMOS techniques indeed remains the most popular techniques for gate construction. We saw transmission gates, we saw a tri-state inverter. Both are very popular in construction of MOSFETs. Then we saw basic layout design techniques. We saw an interesting layout of a 3-input NAND. Again, I would request all of you to take the layout of understanding of the layout of O3 AI as an exercise yourself. And if let's say you have access to some tools that you can draw layout, it would be excellent. Thank you all of you. In next lecture, we would look into how to estimate and calculate the delay of a circuit. So two parameters are very important during gate design. One is the area, other is the speed or the delay of the circuit. Third, of course, there is one more parameter, which is power. But we'll look into more detail into the delay part of the circuit. Thank you.